So welcome to Containers Are Not Your End State, or Were Never Your End State. So my name's Duncan Wynn, and I run platform architecture for Pivotal for the West Coast.
And I'm Will Arroyo, and I'm a platform architect for the West.
And so we're responsible for helping companies transform the way they build and run software. And we do this by helping companies establish a hardened production-grade version of Cloud Foundry. So Cloud Foundry, as the previous talk went through and many other talks have touched on, covers Pivotal Application Service, or PAS, and Pivotal Container Service, so PKS. Now these are two different abstractions. Both these abstractions leverage containers. And there's a reason why you may pick one over the other. And Dave Sire talked about this on Tuesday's keynote. So for this talk, we're not going to go into the differences of why you'd pick one versus the other. I mean, typically it's down to your workload. This talk is going to focus on PKS and Kubernetes and how you start to build an ecosystem to get a production-grade version for Kubernetes. So in terms of our cloud-native journey, our container journey, where are we? So wherever you are along with that journey, I guarantee that this isn't your end state. Building containers, deploying them to Kubernetes is not where you're trying to get to. And just as a quick show of hands, who here would say they're running the majority of their workload in production in a production-grade Kubernetes cluster? Wow, not a single hand. Okay. So we said this isn't your end state. Your end state is much more akin to this. So as a developer, you're developing killer features, you're getting them into the hands of your happy customers who hopefully will be giving you feedback, and you iterate over this feedback loop as quickly as possible so that both you and your company can profit. Now again, I'm stating the obvious here. This is nothing new. You've probably seen 100 slides similar to this. But the reason why I'm laboring the point is I still meet companies who tell me things like, we need to adopt containers by the end of the year. And when you dig into why, when you ask them what business problem they're trying to solve or what technical challenges they have, they can't always articulate how containers are going to help in their ecosystem. So when I see companies run headfirst into a technical strategy, a technical solution, without being able to articulate the problem it's trying to address, I start to think hype cycle. Now, I'm not trashing Kubernetes here. I actually really like Kubernetes. But for those who've been in tech for some time, we typically see again and again this hype cycle where you have to get past this peak of inflated expectations and past this trough of disillusionment where people tend to throw out the good with the bad to some level of productivity. Now, as a side note, this plateau of productivity, good tech should never plateau, so I really hate that analogy. If good tech plateaus, it dies. But nonetheless, we're trying to get to a level of productivity. So where does Kubernetes as a technology fit into this ecosystem? So we believe it's actively beyond the early adopters. There's a lot of people interested in Kubernetes right now. But there hasn't been a ton of negative press, and we're nowhere near that 5% adoption based on the fact that no one in the room raised their hands. But wherever we are on this curve, we really need to get to this productive end stage. So how do we get there? Some of it's down to the technology maturing, so new features and functionality being added to the technology. But a lot has to do with how you go about using and deploying this. So making sure you have a mature deployment approach, making sure you have systematic processes for your data operations, making sure you understand the wider ecosystem, so beyond Docker, beyond Kubernetes, what else do you need to run a production-grade cluster? Understanding your failure boundaries, your security profile, and understanding the appropriate workloads for actually running on Kubernetes. There's a lot of other things you should probably look at as well, but if you get these right, these 5 things, you'll be a long way towards getting there. So the rest of this talk is going to unpack these 5 concepts across 4 core areas: container principles, building and running your container images, and deploying to Kubernetes itself. Each one of these 4 things is quite a meaty topic in its own right, so we're going to just get cracking straight in. There are 2 ways of looking at containers in Kubernetes. There's the thing you actually run. This used to be called a file system. This is your container image or your Docker image. And then there's the management piece, the runtime component. So a Kubernetes worker node has a kubelet, and this kubelet needs software that, amongst other things, needs to start and stop containers or containerized processes. And it achieves this through something called the container runtime interface. So CRI, the container runtime interface, is a pluggable interface, so you can swap out the bits and pieces that actually make this happen. By default, you have a shim at the top, so you have a Docker shim, you have a Docker process, Docker runs container D, and container D spawns run CBAT containers. So there's a lot of different layers here and a lot of moving parts. And it may be a powerful thing that you can swap some of this out, so you maybe use Rocket or Cryo. But if you swap stuff out, you need to know what you're doing. And so it helps to understand that there's not just one thing going on here. There are many things at play, and by understanding this, it will help you debug, and it will help you on your security side.
So like Duncan said, there's a lot of moving parts here and a lot of things to understand. So let's get into some of the common anti-patterns with Docker. So running as root inside of a container is a common anti-pattern. So would you do this if you were running an application on a VM? Probably not, because of the inherent security risks there. So why is this happening so often in containers? And that's probably because some people will argue that if you're inside of a container, you're inside of a contained process, so nothing can happen. But really just a misconfiguration in Docker itself or on the host, any of these things could allow for that process to get outside of the container and really cause some security issues. So let's take a look at how this happens. So changing the user in a container is actually pretty straightforward. So what we're going to do is, if the video starts. Okay, so what we'll do is take a look at a Docker file here, and this Docker file is just going to be adding a user, and we're just using common Linux commands here to add a user inside this container, and then we're using the user instruction inside of that Docker file to set to the user that we just created, and that's Spring1. And what this is going to do is when you start that container, you're now going to, by default, be running as that Spring1 user. So if we then run a container based on this image, what we'll see is that all we have to do, we don't have to pass any commands to it or anything, and if we do a who am I inside of that container, we're now the Spring1 user. So this is really important because this makes your container more secure. But all you're really doing here is limiting the risk. You still need to be careful and have good security practices actually on your hosts themselves and limit permissions to Docker, because you can still do things like this. So if we take that running container that we have and we just do an exec into it, what we're going to see is we can override that user with a user and group ID, and if we do a who am I, we're now root inside that container. So if somebody gets access to your system and can run the Docker command, they can still override the user and get in there as root. So you're going to want to make sure that you're really tight on security at the host level as well. And just one thing to note here also is that when you're running PKS, the VCAP user is also a privileged user. So you're going to want to make sure you're not using the VCAP user inside of that container as well.
So we've covered the container management piece, and we've talked about there's complex layers that are responsible for running your container as an isolated process. So let's look at the responsibility of how containers are actually built. So typically, an image that runs your application is going to have 3 core layers that form that final image. So you start with a base OS, and this is often something like Ubuntu or Alpine, and most likely you'll pull this from Docker Hub, and then it'll be hardened to your corporate standards. From there, you have a middleware runtime layer. This is the bit of technology that runs your application. So it'll be Java or Ruby or some other component. And again, often you have some company-specific configuration and standards applied to this layer. And then finally, on top of that, you'll have your application and all of its dependencies. So in the Java world, that would be like your Spring Boot jar. Now, we talk of these as layers as if it's a stack, but it's important to note that these aren't actually a vertical stack. When you add one layer to your image, it encompasses the previous layer. And this is a crucial thing to understand because you need to use layers very, very carefully.
So when we're talking about layers inside of a Docker container, there's 3 commands in a Docker file that are going to contribute to those layers being added, and that's add, copy, and run. So all of these instructions are going to add to the size of that image you're creating, both through metadata that's attached with each layer addition, as well as anything you're doing inside of those different commands, maybe adding a file or something like that. So let's take a look at a Docker file here. And if we look at this, we're going to see I have 2 of these commands being used in there, add and run. So in the add command, I'm just going to grab the AWS Java SDK. This is like a 400 meg or so zip file. And then in the run command, I'm going to extract it, and then I'm going to remove the zip so I get rid of that extra file. Now, if we look at another Docker file that does the exact same thing, we're going to see that instead of using the add there, we're using run. So we're doing the same thing, but we're using curl, and we're all in one layer there. And you would think at the end, the images should be the same. So if we look at the history of these files, so the Docker history command is going to give you the ability to look at every layer that exists inside that image. And we see the first one that we created, we have 4 layers now. And you can see the top layer is the run layer, and then we have the add layer, and that's about 443 megs. And then if we look at our second Docker image and look at the history on that, we should see that there's only going to be 3 layers. So there's 3 layers because we're not using that add command in the second image creation, and we just have the run there. So what does this mean overall for your file? Your Docker file and your final image size. So what that means is if we look at those 2 images side by side and look at the final size, the first one's 1.8 gig and the second one's 1.43 gig. But we removed that file in both scenarios, so why is one bigger than the other? And that's because if you have separate layers and we added a file in one layer and removed it in another, that file's still going to exist inside of that one layer. Even though if you go onto the file system, you're not going to be able to find that file, but it still exists and still contributes to that final size of your image. So you just want to be aware of these things so that you know when you're adding layers, just use them very carefully. And you can mitigate this happening by using like multi-stage build files or even like chaining run commands together in one run statement.
Okay, so automation is key, and building these containers is no exception. So we tend to have a pipeline for building all your images. And at Pivotal, we have Concourse, so we love Concourse as our CI tool. So typically, this will start with your upstream base OS image. So there'll be a change there, and your pipeline will notice that change, and then grab that, apply all your corporate hardening and configuration, and then create that base OS image. From there, the middleware layer is triggered by that base OS image. And again, this is a one-to-many relationship. So you may standardize on one base OS, but you may have different middleware pieces for different application workloads. So you may have one for Java and one for Ruby. And when they're built, they'll trigger your application tier to be built. And again, there's a one-to-many dependency there. So you may have a Java runtime layer as a single image, but you may have many apps that then get invoked on the back of that.
So during this build process, there's something we can use called build args. And what a build arg is going to do is allow you to make that Docker file more dynamic. So the middleware runtime layer that we were talking about, that might be Java. And you might have a Docker file that sets up your whole Java ecosystem the way you want it. And you just want to swap out versions and build multiple Java version images. So rather than having multiple Docker files, you could pass a build arg in there called Java version, change that version, and then inside of the file, leverage that to pull down the right version that you want. But then we also have in here the AWS secret key build arg. So this is an example of something you're not going to want to do because build args are not secure. I've definitely done this plenty of times, and I'm glad I don't do it anymore because, like, for example, you might access an S3 bucket that's private in a Docker build because you're like, hey, I'm going to pass a password through, but they don't act like environment variables. So let's see why this is insecure. So if we have a Docker file and we pass in a password, and then I'm just going to send that to dev null. We're not going to store it in the container. We'll just send it to a black hole. So if we go and build an image from this, we'll pass it a parameter for build arg, password equals secret123, and we'll build that. So at this point, we should be able to then do an inspect on it. So an inspect is a command in Docker that's going to let you see all those metadata layers in there. And if we grep for password, we can see that password equals secret123 is just right there in the Docker metadata. But what's key to note about this is that this isn't just on my local MacBook. Like if I push this up to Docker Hub and any one of you in the audience just says, hey, I'm going to pull that image down, you can do the same exact command and get that secret. So not putting secrets in the build args is a good idea. Something else that's important in Docker is versioning. So versioning in Docker is called tagging. And one thing that you should be aware of is if you don't use tags in Docker, by default, it'll just throw the latest tag on there. Whether you're pulling or pushing images, it's going to use the latest tag. So in this example here, we've got Ubuntu, and my Docker image, or my Docker file is going to reference, I want Ubuntu. And I'm not specifying a version or anything like that, so the first time I build my image, I'm going to get Ubuntu 14.04 because it's going to give me that latest image. So all my builds are happy, but then what happens is this latest tag is just an alias, so it can be added to anything. So the maintainer of this really determines how this works. And Docker doesn't do strict versioning, so it's really up to the maintainer to determine how all of this works. So that latest tag moves to Ubuntu 16.10, and now all my downstream builds start failing because everything changed in Ubuntu 16.10 and nothing's working. So it's important to know that this is going to continue to happen. But also, the inverse of this could happen. So I could say I want the latest tag, and I might be thinking that I'm always going to be up to date, I'm always going to have my patches, but the maintainer decides the first time they may push out that latest tag. But then you get a new version and another new version, and that latest tag is just going to stay wherever it was last pinned to. So I think I'm up to date, but now I'm a few versions behind and don't have any of my patches. So what you're really going to want to do here is be explicit when using your tags. So I want 14.04, so I'm just going to specify 14.04. That way, as those new versions come out and the latest tag moves with it, I'm always on that 14.04. It's a frozen artifact, and I know I'm using exactly what I want to. So internally at your company, you're going to want to make sure that you come up with a good versioning strategy, and it's extremely important to do this. This is going to let the people that are consuming your images use them more easily, and also prevent any of those unexpected outcomes that we went through. And just make sure you're using those explicit versions when you're building or using images, and that way you can control your patches and upgrades and everything the way you want to.
So once we have our versioned image, your application pipeline can then deploy it to Kubernetes. So again, we pipeline everything. So you have that app image, and that then triggers a deployment to Kubernetes. As part of this deployment, you have some configuration that gets applied, some environmental configuration. And this is important because environmental configuration configs often get overlooked during the build and deploy phase. But your configuration can absolutely break your deployment. And so for this reason, we recommend having all of your configuration by your secrets in a source code repository. So how do you actually deploy your applications? As a quick segue before we start to unpack this, when we talk about the microservices world, you typically have lots, You typically have lots of these small A applications. So discrete units of work that do one thing very well, built by a single business capability team. And all these small A applications tend to work in concert to form this big A application, so something really meaningful like Netflix. So how do you deploy your big A application to Kubernetes? There's two common ways. The first is with Helm, which is a package manager, and the second is with kubectl. So with Helm as a package manager, it can package up all of your app dependencies, all of your individual components as one single deployable unit. So you have a central topology you can just deploy to Kubernetes. And while that's very powerful, Tiller, which is the component of Helm that actually runs in Kubernetes, is considered to be a bit brittle and makes your Kubernetes cluster more vulnerable. And so for that reason, a lot of folks in the Kubernetes community don't actually like Helm. The alternative, using just kubectl outright, it can be a bit more verbose because you may want to deploy everything line by line, and this means when it comes to discovering your big A application in Kubernetes, it's a little bit harder because by default, Kubernetes treats every single deployment in isolation. So there's a way of blending these two approaches. There's a happy medium in that you can actually use Helm outside of Kubernetes to generate all of your Kubernetes objects into a single large YAML, or a single manifest, and then you can take that single file and have a single operation to deploy it to Kubernetes. So as you're deploying, there's a concept you need a trusted registry. So typically what will happen is a developer will download their base OS image, they'll download their middleware layers, they'll put their app into that final image, and they'll push it up to a trusted registry, and then from there, you'll have a pipeline which pulls from there and deploys to Kubernetes. Now that's okay, but if you're not actually checking what you're pulling down from Docker Hub, you can find you get unstuck very quickly. So for example, Will and I downloaded the OpenJDK Java 8 JRE image, and we ran a scan on it. We used Harbor, which is our trusted registry. It comes with PKS. And as a result, this image, it's been up for 9 hours. It has 6 high-level vulnerabilities and a number of medium and low vulnerabilities. So it's really not that good. So this is key in that Harbor will scan your images, and you can actually set policies so that certain vulnerabilities and certain images, it will actually refuse to deploy to Kubernetes. In addition, you can actually sign your images as well. And this means that Harbor has signed images and will repeatedly scan for those vulnerabilities. And that helps you have a level of protection for your production-grade cluster. So we talk about being detective, but you also need a proactive stance to baking in security. And so typically, one of the ways we look at strengthening our security posture is you start with your base OS image. You harden that to your corporate standards, and then from that point on, you build every other layer yourself. So stop going to Docker Hub and grabbing up other pieces of technology, just build it all by hand, and put in the security scanning and security governance at every single tier. So moving on to the pipelines themselves, in a traditional push model, we typically see a couple of pipelines. You have your developer pipeline at the top and an operator pipeline at the bottom. So the developer makes some change, they push their change up into your code repo, and then your CI tool, so in this case Concourse, is looking at that repository, sucks in that change, builds your Docker image, and puts it into your trusted registry. The operator pipeline is looking at that registry, grabs it, and then deploys that to Kubernetes. So one consideration and one challenge here is that typically your configuration will be in multiple places, and it may not always be in source control. So another way of doing this is with a concept called Git Ops. It's relatively new, it's been around for a couple of years. But it's the idea of having a declarative infrastructure. The developer flow at the top is the same, but when you put your Docker image into Harbor, it gets pushed into your config repo, and any changes to that config repo, whether it's a new version of your image or whether it's environment changes, get then reflected back into your Kubernetes cluster. So everything from monitoring to policies to config, everything's tracked in GitHub. So it's a good approach forward.
So when you're deploying Kubernetes, there's a number of considerations. So are you going to roll your own? What security practices do you need? What actually, are you going to automate this? Do you need to automate this? So with all the services that you have out there today, there's very limited reasons to be rolling your own Kubernetes from scratch. The risks of just not doing it right are way too high, and there's lots of experts in the community that have already solved this problem and make it easier for you to deploy a secure Kubernetes cluster. So one thing that's kind of different about these services is you need to understand what the service is going to bring versus what you need to bring. to the table here. So for example, EKS is going to manage your control plane, your master nodes, but you're still gonna have to roll your own worker nodes and like patch and update all those things. So if you were using PKS, for example, it's gonna handle all of that for you. And then you also need to consider if you need to be hybrid cloud, you probably don't want to go directly to one IaaS provider. You might want to use something like PKS or KubeADM or RKE. That way you can span multiple clouds. So let's just take a quick look at how you deploy a PKS cluster. So we just run a simple command here, tell it the plan we want, and once we kick it off with those few parameters, this is sped up obviously for the presentation, but it's just going to take some time. You'll have this feedback on it's in progress. If it fails, you'll be able to see that, and then you'll get succeeded. And you'll get an IP of your master node, and you'll have a master host DNS address to go to, and you can just connect directly to that and start deploying applications immediately. This is an entirely configured Kubernetes cluster now. So whichever method you choose, you're going to want to make sure that you're automating everything. Lots of people are using pipelines for their applications, but they don't think about using pipelines for their platform and their clusters. So you're going to want to make sure you're doing that. And you can use pipelines to update your workers if you have to. You can use it to add in security and configuration. All of that can go into a pipeline to automate your actual deployment of Kubernetes. So in that pipeline, you're going to want to do things like conformance testing. So conformance testing is going to make sure that your clusters are adhering to the standards that the Kubernetes architecture SIG has set out. And that's going to make sure you're configured to best practices, and also that your apps can be portable. So any clusters that pass these conformance tests, ensure that there's compatibility across these so you can port your workloads very easily between them. So this is going to prevent that vendor lock-in as well. So one thing you can use is Heptio's Sonobuoy. It's a cool tool out there that lets you run these tests against your cluster very easily, and it'll give you a nice set of results back, what you're passing, what you're failing. You're also going to want to make sure that your Kubernetes cluster is secure. So adding security into your pipeline for this is also very important. Aqua Security makes a tool called KubeHunter. You can point it at a Kubernetes cluster, and it'll go check for vulnerabilities. It also has an active mode, which is a little risky, but it's going to try and exploit those vulnerabilities as it finds them. So don't run it on a production cluster. But there's also, Aqua Security also makes a tool called KubeBench that makes sure that your Kubernetes clusters are passing those CIS benchmarks that are laid out. And you just get results back. So another thing that's really important here is going to be day 2 operations, patching all your hosts and doing all of that stuff. So you just want to make sure that you have a nice automated defined process to do that, and you're thinking about it when you're building out Kubernetes. If you're using Bosh with PKS, this is going to handle all those day 2 operations for you. It's going to update your nodes, update everything for you. And for example, if a node dies, falls apart, Bosh is just going to say, go create a new one. And so Bosh is really going to do for Kubernetes what Kubernetes is doing for the applications.
So just to wrap up, some key takeaways. So you need to choose a deployment method and try and stay as close to upstream Kubernetes as possible. So PKS absolutely commits to this, and then Sonobuoy will actually check for this, so that will help you. Understand your Kubernetes components. So beyond just the worker node and the master node, understand what's going on in terms of what's actually running your isolated processes. This will help you with security. This will help you with debugging. Be careful building your Docker images. Put governance and security into every single layer. And automate everything. So start with your platform, automate the building of your images, automate the deploying of your apps. Once you have this down, repeat again and again, and that will help you get to a good state. So just to recap, we've talked about Kubernetes and containers are not your end state. There's an entire ecosystem of things you need to be aware of to get to that productivity zone. Thank you very much.